Hello, viewers. Good morning. I am waiting for more people to join. Let's see, we're up to 12 viewers. Let's try and get it above 20. Not that there's anything you can do about it. We're at 19 and 20. Okay, I'm going to start. All right. Good morning, class. Just one announcement. Next week, you are going to have a midterm. It won't go on the triad grade. The triad ends on Friday, but that following week we'll have a midterm. It'll be worth 100 points. It's going to be just like the quizzes we do every day. The only difference is that it is going to be probably about 15 or 20 questions. So it'll be a little bit longer. And I'm only going to put content on the midterm up until today's lesson. So this is the last lesson that is going to be on the midterm. I will give you something like 3 hours to complete it once you've started. So I'll give you a full week to work on it, but or a full week to take it any time during that window, but you will only get 3 hours once you've started it. I don't think it's going to take 3 hours, but I'm just doing that in case you need to take a break or you have internet connection issues or anything like that. Okay? So this is the last lesson that will be on that midterm. Okay? So let's just talk about last time, just because that was such an important lesson. I don't know why this thing doesn't focus properly sometimes, and it really drives me nuts, this document camera. So what do you need to focus? Focus. It's not focused. Focus. Well, last time. Okay, so what did we do last time? Well, we learned what a force is, and we learned Newton's 3 laws of motion. So a force is a push or pull. The units of force are called newtons. Okay? As I keep trying to focus this. I don't understand why I can't manual focus it. Maybe I can manual focus it. I'm sorry. I'm just really pissed off that this is not as clear as it could be. We learned the first law of motion, which says that the acceleration is equal to 0. Another way of saying that is that the velocity is constant when the net force is 0. So recall the net force is another way of saying the total force that is acting on the object. I just keep pressing this button because it's driving me insane. So the sort of standard way of saying the first law of motion is objects in motion stay in motion, objects at rest stay at rest unless acted upon by a net force. So the acceleration equals 0 when the net force is 0. The second equation is the most important equation in the course. It says that the net force equals mass times acceleration. We're going to use that equation repeatedly throughout the class. And recall that the units of mass we are using are the kilograms. The third law says that for every action there's an equal and opposite reaction. The mathematical statement of that is the force that Bob exerts on Alice is equal to minus the force that Alice exerts on Bob. Okay, so the third law relates to interacting systems. Okay, if one person is exerting a force on another person. Oh, there we go. It finally decided to focus. Now I can relax. So that is a review of last time. We used Newton's second law to calculate the acceleration, which we then used in a kinematics equation. So this is very useful for that reason. Okay, so today what we're going to talk about is some different types of forces. What are the different types of forces that we can encounter in this class? All right, so that's the topic of today's lesson, and we're going to do lots of examples with different types of forces. So the first force is just an applied force, which I will call F sub A for applied. And applied forces are simply an unspecified force, okay? So if you just push on something, that's just called an applied force, okay? So it's just a force that is put on an object, and the exact origin of that force is not really important, so we just say the applied force, okay? So oftentimes there will be an applied force by someone on an object. The second type of force that I want to discuss is the weight force. The weight force is the force of gravity. Okay, it's the force of gravity. It points downward. okay? And its value is equal to, so the value of the weight force is equal to m times g, where m is the mass of the object and g is the acceleration due to gravity, okay? So if you have let's say you have a mass of 55 kilograms, then your weight is going to be 55 kilograms times 10 meters per second squared, 550 newtons is your weight. Okay. One of the things about the weight force is that the weight force can change from place to place. So as you go from place to place, your weight force can change because gravity can change from place to place. So if you go to Mars, your weight force is going to be different because the acceleration due to gravity is different. But that being said, your mass is still going to be the same because the mass is the amount of matter that is inside you, okay? So if I take you and I move you to Mars, your mass didn't change because you're still the same person, but your weight force would because you're being placed in a location where gravity is different, okay? Actually, there are subtle variations in the acceleration due to gravity across the surface of the Earth. So especially depending on latitude, so whether you're up towards the North Pole or down towards the equator, that has an effect on the acceleration due to gravity and therefore your weight force. Okay. So anyways, that's how you calculate weight force. Another force that is important is called the normal force. Okay, and the normal force I will denote by F sub n. The normal force is the force from a surface. So anytime you are pushing against a surface, that surface is pushing back against you with what is called the normal force. So for example, if you set something on a table, you have the weight force is pushing the cup down, okay? But the surface of the table is pushing the cup up. If we didn't have that normal force, if we only had the downward weight force but no normal force pushing back up, then the cup would accelerate downward through the floor, okay? So what the weight force ends up doing is it prevents objects from passing through a surface. Okay, so the weight force prevents objects from passing through a surface. So we're going to do a couple of examples with the normal force, okay, so you understand how it works. So in particular, what if you are standing on the floor, okay? So you're just standing on the floor. You have a mass of 50 kilograms, all right? What is going to be the normal force in this case? All right. Well, I'm going to draw what's called a free body diagram. So a free body diagram means represent the person as a dot. Okay, represent the object as a dot. And we're going to draw arrows where each arrow represents a force acting on the person or the object, okay? So the way that the normal force works is it always points away from the surface, okay? So if the surface is like this, away from the surface would be directly upward. So then I'm going to label it F sub n. And the other force is, of course, the weight force, the force due to gravity. The weight force is m times g. So the mass is 50. Gravity, if this is on Earth, is 10. So we have 50 times 10 is 500 newtons going downward. Okay? Now let's think about it for a second. If a person is just standing on a surface, okay? If a person is just standing on a surface, they're not accelerating. They're not accelerating. They're at rest. And if they're at rest, according to Newton's first law, the net force is 0. So because the net force is 0, that means that the upward forces had better equal the downward forces, okay? So that means that the normal force and the weight force are equal in size. So I'll put a little slash to indicate that they have the same size. So that means that in this case, the normal force is 500 newtons. So basically, if you put a 10 Newton cup on the table, then you can say that the normal force on the cup is 10 newtons, okay? So oftentimes, the normal force is equal to mg, the weight force. So whenever you just set something on a flat surface, you're going to have that that's true. But there are some special cases where the normal force is not equal to the weight force. So let me go over some of those cases. So we're going to do some more examples. What if you had a person standing on this on a surface, and again, it's a 50 kilogram person. But what if there was an additional downward force, a downward applied force of 70 newtons? So someone is pushing down. I think I have an example in today's quiz where someone is getting a massage, and you know the masseuse is pushing down on the person's back. So that's adding an extra downward force. So what does the free body diagram look like in this case? Well, you have the weight force going down, which is, again, 500 newtons, 50 times 10. You have the 70 Newton applied force going down, okay? And then you have the normal force going up. All right, so what we can see here is that the total downward force is 570 newtons. So then we think about, well, what if the normal force was less than 570 newtons? That would mean that there would be more downward force than upward force, so the person would accelerate through the floor, which is not happening. The person is standing on the floor. What if the normal force were bigger than 570 newtons? Then the person would be flying into the air, accelerating into the air. So the only thing that makes sense for a person just standing on the floor with a 70 Newton force going downward is if the normal force is equal to 570 newtons. Okay? So that's an example. Another example is what if you had a wall like so? Okay, so instead of a floor, it's a wall. And you have a box. And the box is being pushed by a 30 Newton applied force. And let's say that it is a 7 kilogram box. Type it into the live chat if you know what the size of the weight force is on a 7 kilogram box. Okay? Type it into the live chat if you know. So in this case, we have the 30 Newton applied force going to the right. Okay. Which way does the normal force in this case point? Well, the normal force always points away from the surface. So if you have a wall, away from the wall is going to be to the left. All right. It appears that no one wants to participate and type into the live chat the answer to my question, so I will say what it is. If you have a 7 kilogram object, then the weight force is going to be mg, so 7 times 10 meters per second squared. That is 70 newtons. All right. So in this case, the normal force is actually going to equal 30 newtons. Why is that? Because the 70 Newton weight force has nothing to do with the object passing through the wall. What would the weight force cause the object to do? It would cause the object to slide down the wall. Okay, so the force that is actually pushing the block into the wall is the one that has to be countered. Okay, so it's got to be 30 newtons in this case, because the normal force is going to prevent the block from getting crushed through the wall. All right, I hope that makes sense. And we'll do one more example. What if you have a person in an elevator? Okay, you have a person in an elevator, and the elevator is accelerating upward at, let's say, 3 meters per second squared. So that's the acceleration of the elevator. Okay. If we draw a free body diagram for this person, let's again say it's our 50 kilogram person. The weight force is going to be 500 newtons downward. The normal force is going to be going upward, but in this case, the normal force will be bigger than the weight force. Why is that? That is because the elevator is accelerating upward. Okay? So we've got to have normal force bigger than weight force in this case, because if not, the person would not be moving upward with the elevator. So we have net force equals ma. The net force is going to be upward forces minus downward forces. So normal force minus 500 equals m, which is 50, times the acceleration, which is 3 meters per second squared. So that's 150. We add the 500 to the other side, and we get that the normal force is equal to 650 newtons. Okay? So that's the normal force. So oftentimes the normal force is equal to the weight force, but there are some situations where it is not. For example, if you have extra forces pushing on the person, if it's a wall instead of a floor, or if the floor is accelerating. Okay? So there are several cases to consider. Okay. So the next force we are going to talk about is called friction. So friction is denoted by a curly F. Okay. And basically, friction is an oppositional force. Okay, that resists surfaces sliding across each other. Okay, so for example, if I push my hands together and I try to move one hand across the other hand, that resistance is friction. Okay, now there are two types of friction that we want to consider in this class. One type of friction is called static friction. So static friction, static means unchanging, right? Static is unchanging. So static friction refers to friction when two objects are laying against each other, but they're not sliding across each other. Okay? So, for example, if I have this coffee mug, it's on a coaster, and I push on the coaster, I'm applying a force on the coaster, but the cup isn't accelerating to the side. Why is that? It's because static friction is resisting my push and preventing the coaster from sliding. Okay? So static friction is what occurs when there is no sliding happening. Okay? But if I apply a big enough force, it starts to move. But I still am getting resistance. There's still resistance even if the object is sliding. So that type of friction is called kinetic friction. Okay. So kinetic friction means friction while sliding. Right? Kinetic means motion. So that's why that works the way it does. So there is a formula for kinetic friction. So I will denote kinetic friction by F sub K for kinetic. And that formula is mu sub K. So this is the Greek letter mu. It's kind of a fancy M or a fancy U, depending on your perspective. It looks more like a U to me. Times the normal force. Okay, so notice as the normal force is bigger, the kinetic friction is bigger. Okay, so why is that? It's just an experimental fact, but you can try it out yourself. If you push your hands together lightly, it's easy to rub your hands together. Okay, but if you really apply some strength and you really push hard, push your hands together really firmly, you're increasing the normal force between your hands, okay? And it's much harder to slide them across each other. So the bigger the normal force is, the bigger the friction force is, all right? Mu sub K is called the coefficient of kinetic friction. Okay? And it is basically a property of the interface. Okay, so there's a certain coefficient of friction for skin on skin, for example. There's a certain coefficient of friction for tire on road. There's a certain coefficient of friction for metal on ice. So depending on the interface, what two surfaces are coming into contact, you have a different coefficient of friction. Okay. So it's a property of the interface. So you could think about kinetic friction you could think about it as the force that must be overcome to keep something sliding. So if you're not overcoming kinetic friction, what's going to happen is the object is going to slide and come to a stop because you weren't applying enough force to keep it moving. Okay, so you have to apply at least this much force to keep something sliding. Okay, if you apply more than that amount of force, it's going to actually accelerate while it's sliding. So this is kind of the bare minimum to keep it sliding at a constant speed. So static friction is a little bit more complicated because static friction can have a range of values. So I'm going to give you a formula for the maximum static friction. So F sub S for static friction. The maximum static friction, it's exactly the same formula. Mu sub S times normal. So there is a different coefficient of friction. This is called the coefficient of static friction. It's the same formula, but a different coefficient. And these really are different numbers. So you might have noticed this before, but if you are pushing an object, it's more difficult to make the object start to move than it is to keep it moving. So, you might have a situation where I push hard and then it starts to move, and it's easier once you get it going. Okay, you might have experienced this before if you've ever been sliding something that's really heavy. It's tougher to get it started than it is to keep it moving. So the interpretation of that is that the coefficient of kinetic friction is less than the coefficient of static friction. So it's harder to get something started moving than it is to keep it moving. One way that you could think about the coefficient of static friction, okay? One way you could think about the coefficient of static friction is it's the force that must be overcome to budge the object. You know what I mean when I say budge? Budge means something that's not moving, and then it makes that initial to start moving. That's a budge. So to make it start moving, you have to at least apply the you have to at least apply this coefficient or the static friction force. All right, so we're going to do some examples with friction. Okay. So the example is a box on a surface. Okay. So we have a box on a surface. It looks like this. Here's the floor. Let's say that it is a 2 kilogram box. All right. And let's suppose that the coefficient of static friction is 0.8, okay? And the coefficient of kinetic friction is 0.3. All right? And then there's an applied force. I'll call F sub A. All right? So if there's an applied force to the right, then friction is going to point to the left. All right? So if I were to do a free body diagram, remember, we just represent the object as a dot, and we put arrows for each force. So if I were to do a free body diagram, there are actually 4 forces acting on this object. There is the applied force, which goes to the right. There is the friction force, which goes to the left. There is the normal force, which pushes upward on the block and keeps it from falling through the floor. Okay? And then there is the weight force, which is mass times gravity. So that would be 2 times 10 or 20 newtons. Okay? So in this case, this is a box sitting on a surface. There's no complications. So this is that most common case where normal force equals weight force, right? So these two are equal to each other, because if they weren't equal, this box would be jumping into the air or getting crushed into the ground. So the normal force in this case is 20 newtons. Once we know the normal force, we can calculate the maximum static friction. Okay, so the maximum static friction is going to be mu sub s times normal. It's right here. Okay, mu sub s times normal. So mu sub s is 0.8. The normal force is 20. So that says that the maximum static friction is 16 newtons. So in order to make this box move, we must apply at least 16 newtons of force. Okay? The kinetic friction force, all right? The kinetic friction force is going to be mu sub k times normal, so 0.3 times 20, and that equals 6 newtons. So let's think about some different cases. So the first case I want to consider is, what if the applied force is 10 newtons? Okay? What if the applied force is 10 newtons? And let's say the object starts at rest. Okay? Is 10 newtons enough to make the object budge? No, because the maximum static friction is 16 newtons. You have to apply at least 16 newtons to make the thing start to move. Okay? So what's going to happen is, if you apply 10 newtons of force, is the object will not budge. It will not move. And in this case, the static friction, so we're going to have static friction, okay, because we couldn't make the object budge. And the static friction is going to be equal to 10 newtons in that case. Now, why is it equal to 10 newtons and not 16 newtons? This is the maximum static friction. It doesn't mean that that's what static friction actually is going to be. It's the maximum value that it can take, all right? So the way static friction works is it matches you it matches your applied force up to the maximum value, okay? So if you apply 10 newtons and try to pull this box with 10 newtons, static friction is going to fight back with 10 newtons. If you apply 12 newtons, static friction is going to fight back with 12 newtons. If you apply 15 newtons, static friction is going to fight back with 15 newtons. Okay? But it can't go beyond 16. So it matches you up to the maximum. Okay? It would be absurd if, let's think about what would happen if you applied 10 newtons of force and then static friction was 16. That would be like you pull on the box with 10 newtons and friction fights it with 16. So there would be a net force of 6 newtons to the left, which would then cause the box to accelerate to the left. So that would be like you tried to pull on the thing, and when you tried to pull, it accelerated away from you. So that obviously makes no sense, right? You never pull on something and then when you pull, it accelerates away. That's just crazy. So static friction matches you up to a maximum value. So now what if we said, what if the applied force is 20 newtons? Okay. If you apply 20 newtons of force, then that is more than static friction. So the object will budge. Object will start to move. Okay? And if it starts to move, that means we are now going to have kinetic friction. Okay? We are going to have kinetic friction. So, if we have kinetic friction, what do we have? Well, we have our 20 Newton applied force, all right? And then fighting that 20 newtons is kinetic friction, which is 6 newtons. So, if we did Newton's second law, net force equals ma, we can see that the net force is 20 to the right and then 6 to the left. So it's going to be 20 minus 6 is the net force. And that equals ma, so the mass is 2. Okay. So that means it's 14 over 2, which is 7 meters per second squared. So, so the acceleration is going to be 7 meters per second squared to the right if you apply 20 newtons of force. If you apply only 10 newtons of force, the acceleration is going to be 0 because it didn't budge. And the friction force is going to be 10 newtons. Okay? So that's how friction works. We're going to learn one more force, which is called the elastic force. I will denote the elastic force by F sub E, and it is the force from an object that is deformed. Okay, so when I say deformed, I mean it could be stretched. It could be compressed. It could be twisted. So anytime you take an object and you distort it from its natural shape, you're going to get an elastic force. And what the elastic force does is it tries to get the object back into its original shape. So a really good example is a rubber band. You take a rubber band and you stretch it, okay? There's an elastic force that tries to bring it back to its original state, okay? If you take a spring and you compress it, there's an elastic force that's trying to get the spring back to its original position, okay? So we would say that it is an oppositional force. Okay? Just like friction, it's an oppositional force. If you try to stretch, it's a resistive force. You try to stretch a rubber band, it pulls back to its original position. You try to compress a spring, it extends back to its original. So the formula for the elastic force is K times X, where K is called the stiffness, okay? And it is a property of the object. So it's a property of the thing that is being stretched. Different springs have different stiffnesses. Different rubber bands have different stiffnesses. The stiffness can depend on time. The stiffness of the elastic band in your underwear becomes less and less as time goes on because it's gone through the washing machine, it's been stretched, and because you've worn it again, several times. So it's a property of the object, the stiffness. Units of stiffness are called newtons per meter. Okay. X is called the extension, and it's basically the amount stretched beyond taut. And that's important, beyond taut. So for example, what if I have a rubber band that is 10 centimeters long? Okay, so you have a rubber band has a 10 centimeter length. And what if these are the two ends of the rubber band? Okay. The two ends of the rubber band. What if the two ends of the rubber band are 5 centimeters apart? In that case, the rubber band is not taut. Okay. So in that case, X is equal to 0 because the rubber band isn't being stretched. Okay. What if I take the two ends of the rubber band and I now make them 10 centimeters apart? So this is X equals 0. This is X equals 0 as well because, basically we've stretched the rubber band as far as we can. We've moved the ends of the rubber band as far apart as we can without stretching the rubber band, okay? But what if we now take the rubber band and we stretch it so that the total length is now 17 centimeters, for example? In this case, we would say X is 7 centimeters because we've gone 7 centimeters beyond taut. Okay? So let's do a really quick example and then I'll be done. What if we have a scale? Okay. Has stiffness 80 newtons per meter. A scale is basically a spring, right? And the weight of the object is related to how much the spring stretches. So a scale has a stiffness of 80 newtons per meter. You put some apples on the scale, and the spring extends 0.03 meters. What is the mass of the apples? Okay, so how would you solve this problem? Well, you have so basically you have the scale that maybe looks like this. Scale has an apple in it, like that, and then the scale has all of these, like that, and then there's a spring. That's how a scale works. So there's a weight force pushing down, which is mg, and there is an elastic force holding the apples up, which is kx. Now, what is kx in this case? It is going to be 80 times 0.03. All right. So that is going to be 2.4 newtons is the elastic force. And these two forces have to balance each other because the apple is on the scale and it's not accelerating up or down. Okay? So our elastic force has to balance the weight force. So we have 2.4 equals m times g, which is, if this scale is on Earth, it's going to be 10 meters per second squared. So we get that the mass of the object is 0.24 kilograms. All right? So that's about half a pound of apples. All right, that's my lesson. I will see you in the Zoom room. Ta-ta for now.